Okay, here's the Crank-Nicholson method. So let's directly see how it can be derived. So remember, we have this, we can take basically forward in time step, and or we can consider the implicit method. So in the implicit method, notice that we had this right hand side evaluated at time step n+1, and the explicit scheme, right? So this was our explicit and implicit schemes. We just write them as before, and basically we will average them together, these two equations, and you can see that we still have the same thing on the left hand side, and on the right hand side we are averaging over these central difference approximations evaluated at time step m or m+1. Okay, so the rest is actually quite similar. You just need to collect everything that you know on the right hand side, and what you don't know and you are trying to calculate should go to the left hand side. So if you do the simple rearrangement here, some algebra, which I'm gonna skip here, this gives you all the terms that you don't know, and we are trying to calculate the terms which has time step n+1, and everything that we already know are calculated on the right hand side, or they are combined together. So again, you can notice we have the, as usual, this alpha constant, delta t over delta x squared. So basically it's the same representation. Now we can move towards the matrix representation, and we can put everything that we know trying to represent in a very simple and compact final form. So in this final form, everything we know will be put together under this vector b. Okay, so the elements of this b are actually z, and this is how we get the elements of z. Okay, so you can look at here. So these are the elements of z, basically, which are written here. So you can directly compare. The only thing is we combine this term and this term here. Okay, so this is together our right hand side, basically. And on the, of course, left hand side, we have these n+1 terms. So they are going to be represented together using this vector. And we need to have a three-diagonal coefficient matrix. Again, you can notice that this is the n term, so that's going to be on your main diagonal. And this is the n-1 term, so that's going to be the shifted by one level from the main diagonal. And you can see this is +1, which is minus alpha over 2, so that's going to be plus shifted upward diagonal term. So this is going to be your coefficient matrix, which is a three-diagonal matrix C. And basically, once we set up everything, the only thing remains is our boundary conditions. So these are separately added for this right hand side. So the boundary conditions comes here. Okay, so this completes the main representation, and basically we can solve again using the LU decomposition, because notice that everything is boiled down to this system of equations here. So this is a vector, and we have a vector, we have this matrix times the vector of unknowns, basically, and you want to solve this equation for un+1. Okay, so we need to repeat this solver, this three-diagonal system with this coefficient by applying the LU decomposition to this three-diagonal matrix C. We can solve the values of un+1 at each time step.